by Bharathasan University. In this connection, I am happy to introduce you today's speaker, Professor Detuning Ray from Indian Association for the Cultivation of Sciences. Before to hand over the session to him, I wish to read out his biodata in a very brief manner for the sake of our MSc students. Professor Ray started his career as a lecturer at Jaipur University and joined as a senior lecturer at the Indian Association for the Cultivation of Sciences in the year 1986. For the past 35 years, he is serving to the institution at various capacities. His academic credentials are very shining. He has received several awards, in which I point out only few. He received the Young Scientist Award from Indian National Science Academy in the year 1984. He received the highest prize, which is being awarded for science in Indian soil, namely Shanti Swarup Patnagar Prize from CSIR for his scientific discoveries. He is also an elected fellow of the Indian National Science Academy, New Delhi, and Indian Academy of Sciences, Bangalore, and West Bengal Academy of Sciences. Besides the above, he is an inspiring teacher also. We are very fortunate to have him today and can hear his lecture. The students, if you want to read out or want to learn more about his work, please visit his homepage or please write to him. With this short introduction, now I invite Professor Ray to deliver his lecture. Over to you, Professor.
Thanks to Professor Senthil for his kind introductions. I'm extremely thankful to you for your kind invitation and your department of Nonlinear Dynamics, which is unique in the country. As I see that we have seen that mostly the Nonlinear Dynamics is practiced normally in the Department of Physics or Chemistry, but this is a place where there is a Department of Nonlinear Dynamics. This is somewhat very special for in the context in India particularly, and particularly thankful to this department for their kind invitation to this lecture. So let me begin with what I'll be talking about is the following thing. So can you see this? Can you see?
No, not yet.
Not yet. Okay.
Detuning, you have to share the document.
I will come to this. I will come to this. Present now. It does screen. Now, can you see?
Yeah, it's coming up.
It is coming up. Okay.
Yeah, now, yeah, it's
now it is full screen. Is it okay now?
Yes, perfectly okay.
Perfectly okay. So I will talk about this anti-resonance in particularly nonlinear dynamics and some aspects of spatially extended systems particularly, and as you will see that this is an area that we have been working for some time, for a couple of years, and as a part of study of nonlinear dynamics. And the idea is the following. So just since there are many students in the audience, and it would be better if we start with a brief introduction to what anti-resonance is, and from that. So let me begin with first with the first slide. There's a concept of resonance, and as you see that the physics begins with harmonic oscillator, and so that's the standard paradigm for the basic science in general. So and all of us are really acquainted with what is called resonance, and this is basically the response amplitude. Sorry, there is some enhancement of response amplitude with respect to a certain parameter, and if you work it out for a linear harmonic oscillator, which is damped and at the same time driven. So this is a damping term. Gamma term is a damping term, and there is a driving term. And if you take care of the sustained oscillation for this particular oscillations and find out this complex response function that x of omega is a function of omega, and you will see that there is a resonance I said when you try to match this omega with respect to this omega 0. So that's at omega equal to omega 0, you have a sharp resonance, and that lies in the heart of physics. So we all know about that. Now we come to the question of what is a counter resonance effect, which is that this is a resonance effect. This is an enhancement of a particular resonance amplitude, the response amplitude at a particular frequency. Now, what happens when we talk about the anti-resonance, which is basically a counter resonance effect, and what this is all about is the following. We consider the same harmonic oscillator, and the damp, and both of there are two oscillators and they are coupled. So 1 and 2 are the two oscillators which are coupled through some coupling constant G, and when they are coupled, and at the same time you drive one of the oscillators and not the other. So that this red oscillator is not driven, but this blue oscillator is driven oscillator, and both are actually damped almost in the same way. And if you look at it, then you calculate this particularly the amplitude, and you will see that there is a particularly for the second oscillator, you will find the two resonance peaks. That is usual resonance appears at the two frequencies. And also the same two peaks appear for the oscillator 1 also, and at the same time in between the two resonance there is a minimum or a dip in the response amplitude. That's a very interesting thing, and this is basically the called anti-resonance, just in tune with this, just as a counter effect to this resonance. So this is somewhat a very peculiar thing, and it means that whenever you have a coupling between the two oscillators, and you try to drive one of the oscillators, then it seems that one of the oscillators which is being driven and some sort of anti-resonance peak, and it almost gets stationary in the entire process, although this is driven. Now, to analyze this particular case, what one does is the following: we express the actual variables x1, x2. In terms of x1 and plus x1 dot, and in terms of alpha 1, alpha 2 complex functions, and then what you try to re-express this the equations in terms of the alpha 1, alpha 2, the new variables, complex variables. And what you do in the process is you apply what is called rotating wave approximation. All that means you try to avoid this kind of high frequency oscillation term or non-resonant terms, that is 2 omega, or appearing at omega 0 plus omega 1 or omega 0 plus omega 2. So if you work out this particular thing, then you can express the same two equations in terms of the amplitudes, in terms of the complex functions, that is alpha 1 and alpha 2, and the time derivatives, and they are as follows. And just apply your steady state condition and try to find out this complex amplitude, and they appear as the steady state amplitude appear as the simple this expression, which is a function of the two denominators, delta 1 and delta 2, but delta 1 and delta 2 are basically the detuning factor which you when you try to tune your oscillator with respect to the frequency omega-1 and with respect to omega-2 for the two oscillators. So delta 1 and delta 2 are the detuning factors, and when they are very close to 0, you see these resonance peaks. But in between the two resonance peaks, you will see one sharp dip due to delta 2 for the oscillator 1. That is for this oscillator. And another interesting thing is that there is the strong difference in the phase of the two oscillators for the blue one and for the red one. The oscillators show the remarkable phase shift for the oscillator 1. So that's another interesting hallmark for this kind of anti-resonance behavior. Now, the question is, with this very brief introduction, this is an introduction that one can have from the usual Wikipedia or many other references that if you can go through the literature, and it has a lot of applications, particularly in engineering, civil engineering, when you have a number of coupled buildings, and if you apply a particular field, then one can actually this particular drive can actually interfere with the coupling so that one gets separated and it remains almost in a stationary state. So one can stabilize a system in a multi-component system, and for which it has some interesting applications in civil engineering field, and also this has also been applied in the field of cavity quantum electrodynamics cases where when actually studies a photon interacting with a two-level system. So, and this has been done by Rempe's group in 2014. So this has also been observed in radiation matter interaction problems and so on. So it is basically why we see this anti-resonance. As you can see that this is basically an interference effect. It is a destructive interference between the two things. One is a coherent drive that I'm driving one of the oscillators, and the coupling. So the coupling and the drive, they actually interfere in such a way that one of the oscillator goes over to a stationary state, almost in a stationary state, and other behaves as usual. So now the question is can this destructive interference be optimized or controlled by some other means? The example that we cited is basically concerns one thing, that they are linear oscillators. So what we'd like to do, we'd like to see the interplay of some kind of nonlinearity embedded in the system itself, and which is a characteristic of the system. And what we would like to do, we put some extra high frequency field in just what we do in the case of vibrational resonance and so on. So it's this high frequency field plays a role of noise, and as we do also in the case of stochastic resonance, and here this sort of what we are focusing at is basically an interplay of this nonlinearity and high frequency field. So let us start with this particular model. So we have just modified this model by usual linear model by these two terms. That is a linear oscillator goes over to a nonlinear oscillator. So beta 1 is a nonlinear coupling term, and beta 2 is another nonlinear coupling term. It's a cubic term. So the cubic nonlinearity is there in the dynamics. And what we apply further is G cos omega t, capital omega t, where capital omega is basically the high frequency, which is much larger compared to this small omega, which is particularly used to study in the case of anti-resonance that we had seen earlier. So this is basically there are two things that we have introduced: this nonlinearity in the dynamics and the high frequency field that has been applied from outside for both the oscillators. Now let us see that because of this, because of the introduction of this high frequency field, there are two time scales that are actually evident in the dynamics. The first one is omega, capital small omega t, and another is the capital omega t. So what we do, just in the spirit of Blackman perturbation theory, we just identify two time scales in the dynamics and try to separate out the contribution of x from in capital X and psi 1. One is a high frequency component, and there is a slow that gives a slow dynamics. So x1 and x2 are expressed in as a sum of the slow part as well as the first part size. So x is the slow part, psi is the first part, and we use the usual perturbation theory to eliminate this fast motion. That is, we average out this particular effect, and in the process of averaging, what we see that the averaging over psi is particularly 0, and all the odd terms are basically 0. And but the square of psi's are particularly non-zero, and they are actually containing this interesting factor that is this G, which is basically the strength of the rapidly varying field, and that and this capital omega is the frequency of the rapidly varying field. So this G and omega are particularly influencing this psi square average, and that coupled with this nonlinearity actually shifts this original frequency to some other values. So omega 1 and omega 2 are the frequencies, original frequencies. They get shifted because of this interplay of nonlinearity and as well as this high frequency effect. So it is basically the interplay that has been displayed in this particular term. And so the point is that these omegas are actually are getting modified, and we will see that they are the main contributor to the effect of this vibrational resonance, particularly that we'll be looking for. So the next thing that one does is the completely usual thing, that we try to linearize the dynamics around the steady state and express the small perturbations in terms of y1 and y2, and we can express this in terms of y1 and y2, and the new frequencies in the linear dynamics are expressed in this way. They are the shifted frequencies from the original one, and they are the usual thing. Now and as usual, we go over to the complex variables from y1, y2 to alpha 1 and alpha 2 using this new frequency omega 1 and omega 2, and therefore then you apply the steady state, the usual technique that you follow, and try to figure out the complex response amplitudes. So once these complex response amplitudes are there, and we can see that once these complex amplitudes contains the interesting factors that they are, that is delta 1 and delta 2, they are basically the actual resonance amplitudes. They appear as such. So and delta 2 appears here, and you can see that they are particularly giving the analytical expressions for the anti-resonance, both vibrational resonance as well as anti-resonance peaks. So if you try to actually calculate this for the specific values of the high frequencies, high frequencies omega-1, and you see the response amplitude for the undriven. This is for the undriven oscillator. You see the usual vibrational resonance when we plot the response amplitude as a function, not as a frequency, but as a strength of the high frequency field. In this case, we see the two peaks in this case, and they correspond to usual vibrational resonance. And in between these two vibrational resonance, you see that there is a sharp dip, and this is this particular dip is vibrational is due to anti-resonance kind of thing. And that's an interesting thing. And you can also do the signature of this in the phase, the response phase, and the response phase, and there is a large shift in this particular case. And once we do this for the usual for the linearized dynamics, this is fine. But one needs to ascertain this particular case when for the actual dynamics of the system, when we have not made any linearization kind of thing. So for this particular case, we have seen that in place in this particular case of a driven oscillator, you see the same kind of vibrational resonance, and in between the vibrational resonance, there is an anti-resonance peak that shows here at some value when you plot it over a range, large range of the strength of the high frequency field. And and at the same time, we have this usual case of the resonance, or the case of undriven oscillator. And so the more or less this is qualitatively there is some agreement, and we can see that there is that indeed there is something called the vibrational anti-resonance, just as a counter resonance effect to what is called a vibrational resonance. And this the agreement between theory and numerics can be better understood if we try to look at the G minimum, that is the minimum value of the strength of the rapidly varying field at which this vibrational anti-resonance occurs as a function of the frequency of the rapidly varying field. And in this case, you see that there is a comparison, and this is what is the theory. The blue line is for the theory, and these are for the usual numerics. It's more or less a good agreement, and same agreement can also be found once we plot it with respect to the nonlinear parameter, when G minimum for this case is plotted as a function of this nonlinear coefficient, and there is more or less some sort of good agreement. And so the idea is this, that the rapidly varying field interferes with the various frequencies because of the nonlinearity. Because since it is a nonlinear system, we know that lots of frequencies are actually operating in the system. And once we apply the high frequency field, then that rapidly varying field interferes with this, high frequency generated, and they actually interfere on a very fast time scale. That is one thing that one has to recognize. And but the rest of the thing, that when we take care of the slow dynamics, for which we see that the low frequency drive, that is that is the usual small omega t time scale. So in that low frequency drive destructively interferes with the coupling on a slow time scale. That's the usual thing, and that causes this vibrational anti-resonance. That's the main physics is there. So the essence of this destructive interference that actually appear here, but they are manifested not in the plot of the response amplitude frequency plot, but in the plot of response amplitude as a function of the strength of the high frequency field, that's why it is called the vibrational anti-resonance rather than the usual anti-resonance case. But again, this is a case of a coupled oscillator, and the fundamental physics of the destructive interference of coupling and the driving, that is almost there always. So with this brief let us now come to another kind of anti-resonance, which we can find in coupled reaction diffusion systems. So, as you know, that the reaction diffusion systems are the systems where you have a chemical reactions occurring at the various places, and the different space points are connected through some sort of diffusion. And this diffusion, and because of this coupling to the diffusion, we call it the reaction diffusion system. And the reaction diffusion systems are actually considered for simple reactions, particularly the reactions of intermediates. We know that in a particular chemical reactions there are reactions, reactants, and there are products. So in between the reactants and the products, there are a lot of intermediate states. So these intermediates actually plays the major role in the game in nonlinear dynamics, and they are actually the main players, and they actually when the reactions get coupled to this diffusion, and we call that the reaction diffusion system. So whenever we are talking about a reaction diffusion system, don't think that this reactions is the reaction between the reactants or the reactants and the products. So it is basically the reaction of intermediates. So the one or two intermediates are mostly identified. Their behavior is interesting, and we try to look at that particular look at the dynamics of that particular behavior through various kinetic experiments. And experiment tells us and what should be the reaction kinetics, and from that reaction kinetics, what we do, we couple the dynamics. So now the thing is that anti-resonance that we have seen here is between the destructive interference between the coupling between the two different systems, and a coherent drive by which you are driving one of the systems. Now this interference particularly can cause the difference in stability of the two subsystems, because you have two subsystems in a coupled system, and whenever you are trying to stabilize one of them, but one of the other is still other still remains in an unstable state. So that's a very peculiar thing, a coupled system which is a stable state, which goes over to a stable state, and other system which does not go over to a stable state but some sort of non-stationary or some sort of unstable state. So interesting kind of behavior. So what influence does it have on the spatially extended or the coupled reaction system? So that is our main goal in this particular chapter, study. So the thing is this, that we consider this coupled reaction diffusion system. So this is a diagram, schematic diagram for the chemical reactions in the two layers. So we have a layer 1, we have a horizontal layer 1, and another layer horizontal layer 2, and we have the two species U1, U and V are the two species, and they are actually interacting in this one in the top layer, and another is interacting in the bottom layer. So U1 is the concentration of U in the layer 1, and V1 is the concentration of V in layer 1, and the same is true for U2. So the U1P undergoes chemical reactions, and at the same time they diffuses horizontally across X and Y in both these planes, in the upper plane and in the lower plane, bottom plane. Now, in between these two layers, there is a membrane, and this and we have a coupling between these two layers, and the coupling is only through one of the components U. So the U1 and U2 are coupled. This coupling term is basically U1 minus U2 minus U1 and U1 minus U2 as these two coupling terms. So the reaction. The diffusion system that we are considering is described in general by this kind of equation, and at the same time, what we do we drive drive the upper layer reaction component U1 by some external force. 2g sine omega t is basically the external drive with which we can actually excite the system in the upper layer, but not the lower layer. And this transverse coupling actually connects the two layers through some sort of diffusion. So now, so this is basically the diffusive coupling because of the concentration difference in concentration between U2 and U1. So that's the thing. So this is the reaction diffusion system. So this is the kinetic equations F1. So this is written in a very general term, and this is a diffusion term. So the diffusion coefficient for U, and this is the usual coupling term with the other layer, and G is the usual driving term, and again this is G is the kinetic term for V, and this is a diffusion term for V, and the same is true for U2 and V2. So with this with this we now go over to the searching for the steady states. So what are the steady states? We find out the steady states, and also we apply spatio-temporal perturbations and type, and try to figure out the dynamical equations in the Q mode, Q spatial mode, and that is U1 tilde, V1 tilde, U2 tilde, V2 tilde, basically are the equations of motion for this. So they are the linearized dynamics that are being exploited, and the stability conditions for the homogeneous steady state is given by this usual expressions, and Fu and Gv are basically the derivative with respect to the reaction components and evaluated at the homogeneous steady states, and this is negative and this is positive, and that ensures the stability of a homogeneous steady state. And from these two equations, what we do, we eliminate U1 and U2 in the usual way. So if you eliminate this, you have the two equations, but second order equations, that is U1 double dot and V2 double dot. So you have the two equations, and you can see that they are very simple looking equations, and they looks like an harmonic oscillator, coupled harmonic oscillator kind of equation, and which is driven at the same time. There is a damping term, there is a damping term here, and the damping terms are basically damping terms, and the frequencies are basically dictated by the nature of kinetics and the coupling of the system parameters. So, but nevertheless, it is basically the same coupled oscillators, but the coupling here is not only through the coordinate, that is V1 is coupled to V2, but V2 dot also. So it is both coordinate and momentum kind of coupling that operates here, and usually V1, V2, V3, and VD, etc. The usual complicated functions and ignore both of the this. So the ultimate the thing that boils down to the fact that they are basically described in terms of simple harmonic oscillators, coupled harmonic oscillators, and the coupling is done through both through the coordinate as well as the momentum sort of thing. And and if you go over to this again to other parameters, the gamma 1 and gamma 2, the complex variables, and then we go over to this. This should be gamma 1. Sorry, there is a printing. There's a misprint, the typo error here. Alpha 1 should be gamma 1 steady state, and this should be gamma 2 steady states, because this is gamma 1 and gamma 2. And these alphas are to be avoided because they are basically the the coupling parameters for the problem. So now once you see that once we calculate this response amplitude, they appear exactly the same structure that we have seen earlier in this the two cases when you have the usual resonance denominators for delta 1 and delta 2 and so on. So you have this sort of the usual behaviors that we can see, and if you plot it, then before plotting we need so up to this we have a perfectly general theory, because we have not made any special choice for the chemical reactions. So it is in general true for arbitrary chemical reactions and diffusion. So now we go over to a particular typical case which has been experimentally studied also, and this is a Gray-Scott model. So Gray-Scott model basically is considers a simple chemical reaction that goes over from it is a chemical reaction between U goes over to P. So U is the reactant, it goes over to the product. And in the process, what it does, and it converts V, 2V to 3V. So it is a cubic autocatalytic reactions. As you can see, there is a term U times V squared term are there. U times V squared terms are basically generic for this sort of autocatalytic behavior. So if you sum the two reactions, it means that you have a V and a V, so 3V, and here is 3V cancels. So U goes over to V. That is the ultimate reaction. So but in the V is basically the intermediates, and they are, and it's an important player in this particular game. And U and V are basically the chemical reaction components, intermediate components that particularly are interest to us, and also to the experimentalist. So and at the same time, what one does, you carry out this you just carry out this reaction in open flow reactor, where you supply this particular V and remove this, but remove the product from the 2K. So K1 is the removal rate. K1 is the removal rate, and S1 is basically the supply rate which you are supplying your S. So there is a supply as well as removal in the entire process, and there are two parameters for this problem. One is the supply rate parameter, other is the removal rate parameter, Q1, S1 and K1. So what one does is that one applies this sort of external field in the upper layer, and see. And also try to find out what is the homogeneous state. Homogeneous state is the 1010 state, and 10 is the usual state, and they are the usual specified parameters for the entire problem. And this has been taken from this particular paper, the Pearson paper in Science in 1993. This is a well-known parameter set. So with this, we find out that the theoretical analysis tells us that there is a sharp anti-resonance defect at near about 0.07 frequency. So when the frequency is something around 0.07, and you see there is a sharp anti-resonance dip here, and particularly for the top layer oscillator, and the top layer oscillator is particularly subjected to this kind of periodic drive, and which is coupled to the lower layer, and the lower layer does not show any anti-resonance at this particular point. So, let us try to figure out this particular, let us try to remember this particular figure, that is 0.07 is the frequency omega, at which we expect some sort of anti-resonance. This is the theoretical predictions that we can think of. And so now we go over to the full numerical analysis of the problem. So what we do, we start from the very low frequencies, and the low frequency as low as 10 to the power minus 9. So with this, you simulate the reaction diffusion system over a grid of 250 by 250 grid, and you see that you try to follow the different, you try to have the snapshots of the reaction medium of the top layer and the bottom layer in this way at different times. So it is at 10 to the power 4, it's 10 to the power 5, 10 to the power 6, and 10 to the power 7. You will see that that at some point that they both appear in the same, these ultimately settles down to this kind of structure, some sort of patterns that you can see, the stripe-like patterns in both layers, which are almost identical. And if you follow follow the actual chemical oscillation at a particular site, say 125 by 125 grid points, and if you try to find out what is V1 and V2, we can see this sort of oscillation continuously persists and as time goes on. So this is at 10 to the power minus 8, and if you and if you go over to an intermediate frequency range 10 to the power minus 5, you'll see that once you start with this at 10 to the 5,000 time unit, then you go over to this case, and after some time you have a completely homogeneous steady state system. On the other hand, you have in the bottom layer, you will see this particular pattern. So this means that the upper state gets stabilized, although it is driven by an external force. And if you look at the same V1 and V2, and you will see that particularly for the upper layer, this settles down to a particular constant value all throughout from 10 to the power 6 to 10 to the power 7. It remains stationary, and you see that some sort of a completely homogeneous steady state. And in contrast to this, you see when you look at the other oscillators, it is continuously the V1, V2 is oscillating, and finally this remains in an unstable state. So this state remains stable, goes over to a stationary state, stable stationary state, but this state remains unstable and shows a typical pattern-like behavior. So it is at 10 to the power minus 5. So if you go to 10 to the power 3, still higher value of frequency, then you will see that the same thing happens here. This settles down to almost to zero, from the beginning, and to an extent of 10 to the power 7 time states, so to the time up to this time. So the upper layer settles down to a homogeneous stable steady state, but the lower layer still remains unstable and shows typical pattern. And the same thing can be simply shown from here there are small oscillations you can see here also, but grossly one can look at the typical pictures of the two layers, and they appear so different. So this is 10 to the power -3, an intermediate frequency range, and so this is a this is a typical example of a spatio-temporal anti-resonance that you can see. And the same thing continues here, and when you go over to 10 to the power, when it is 0.08 frequencies of this kind, the upper layer settles down to a constant value, and you see a homogeneous steady state, and in the lower state you have the completely patterned state that is apparent now. So it is in the intermediate frequency range you have a spatio-temporal anti-resonance, and the high frequency, when you go over to high frequency, say omega equal to 0.2, and you will see that you are back in the game. That is both the systems, so both the layers appear unstable, and they show typical patterns in this case, and that's an interesting thing. So so in the intermediate range, you will see that both the oscillators, out of the two oscillators, one oscillator behaves in such a way that the drive actually interferes with the coupling, and that makes it completely in a station, make the state stable and stationary, and you see that the other state still remains non-stationary. So that's an interesting feature that we can see here. And so that we change over to the high frequency mode. And if you go over still to higher frequency omega equal to 1, the same thing persists when the oscillations and both the layers continues, so the V1 and V2, they continues, and the top layer and the bottom layer both show unstable nature, and so typical spatio-temporal patterns at omega equal to. So over a wide range of frequency, what we see that there is an intermediate frequency range over which we can actually find out this sort of anti-resonance behavior, and outside this particular domain, both the systems are unstable and show typical formation of patterns. Now, up to this, we have considered the coupled systems, that where we see this kind of anti-resonance behavior that is being observed. That is one case we have seen a vibrational anti-resonance kind of behavior in a coupled system, coupled dynamical system, and in the second case we had actually considered spatio-temporal systems, and when we have a complete drive when we have interference effect between the two things. So one is the coherent drive, and other is the coupling. So that makes the system, one of the system, completely steady. But now we ask the interesting question: can anti-resonance occur in a single-driven system? Then, so the paradigm with which we started actually it does not tell us like this, but let us see that yes, this is a possible thing. So just to have this idea a little bit explained, what we'd like to do, we begin with a toy model. We consider a harmonic oscillator and which is parametrically modulated by a particular frequency omega t. So this is the harmonic oscillator that once a is 0, if you put a equal to 0, you see this is a complete harmonic oscillator. But once you add a sine omega t kind of thing as a square, then it means that inherently you are exciting the system with 2 omega. that is sine square omega t. It is something like. Now, if we want what is the condition for sustained oscillations, that we start with the answers that x equal to a cos omega t, where omega is the frequency of oscillations for x. Then what we do, we neglect the non-synchronous terms and other things and put that inside instead of x, and just simplify it a little bit. Then we see that there are two terms. There are two exponential terms. One exponential term is e to the power I omega t, where omega is the frequency of oscillations with which x oscillates, and other is the 2 omega minus capital omega. So 2 omega is basically coming from the square term, sine square term, and so these two, if we have a closer look at these two exponential terms and what this means, that yes, that one can have sustained oscillation once I can equate this capital omega to this 2 omega minus omega. It means if we adjust this particular frequency this omega in such a way, this omega is equal to 2 omega, that means omega equal to omega, then you have the two identify two different kind of transitions. This actually is an oscillating term. That means system gets polarized by this kind of oscillations, and is a polarizing oscillation at a frequency capital omega. And another is a parametric transition, and this is basically you excite 2 omega by 2 omega, and you are actually de-exciting with respect to this capital omega. So 2 omega minus omega, when omega is equal to this, then omega equal to omega. So there is an interesting correspondence. This is a direct transition. So you go over from the lower level to the upper level through this kind of transition in quantum mechanical term. That is, I just excite the system and it absorbs, and then it gets a higher frequency and goes over to the higher level. And here you are coming to the same level, that is the same level, but through a virtual state noted by this dotted line, and you go over to excited state 2 omega and jumps back to your this excited state. So that means that you are you are actually connecting the two states either by this capital omega or by 2 omega minus omega. One either by the direct transition or by this parametric transition. So that now the question is that can these two transitions interfere destructively? So is it possible that these two transitions can destructively interfere? And if they can, then we expect that we anticipate that some sort of anti-resonance might actually occur in this particular case. So this is a hunch. It is an idea that we are trying to work it out. So we again start with that. Start examining this particular scenario in a driven gray spot system. That is the same gray spot system as I discussed earlier, and this is that is a cubic catalytic reaction, U V square kind of kinetics, and that is the kinetic term. And at the same time, you have this supply term as well as this removal term K. So supply term is S0, and this is another is removal term. They are the only two parameters for this chemical reaction. And what you do, we just modulate this particular supply rate S0 by some A cos A sine omega t. So the supply rate is being modulated by some means, and the removal rate is left as such. So with this simplest modification, what we do, we have a system. We just think of a system and linearize the dynamic. We have the same steady state 1, 0, and try to find out the equation for after eliminating after eliminating u, as usual, we have an equation for v. So this is an equation for v, where the usual gamma, this is the damping term, gamma 0 is expressed in terms of the system parameters as well as the diffusion coefficients for the u and v, two reactants, and q is the wave vector, and so on. And omega square is basically again a positive term that you can see is basically the oscillation frequency that you have. But the interesting thing is that you have a sine squared term, that is the 2 omega excitation is there. So that is an interesting feature that is contained in this particular case. And with this we go as usual. We just analyze it, express it in terms of this complex amplitude, and try to find out the response amplitude, or the real part of it, and find out that there is an interesting resonance, anti-resonance peak at this particular value here. But here there is only one oscillator there, but there are two different kind of transitions, and we are trying to look for any interference effect. And you see that there is certainly an interesting sharp dip at some frequency omega. And now we look at this particular, with that particular omega value, we try to find out we try to carry out the numeric analysis of the original reaction diffusion system. So what we do, we have the usual this supply term driven by some sin omega t kind of thing. And we find out how this V component look like. So we take the snapshot pictures at different times, at 10 to the power 3, 10 to the power 4, 10 to the power 5, 10 to the power 6, and so on. So once we see this sort of, see there is a spot-like patterns that they appear at some value, and when the frequency is 0.001. So at a very low frequency, there is a simple pattern-like structure, and both U and V oscillates as usual. And if you just put the value to 0.01, then the same thing continues, and we have again the up to 10 to the power 6. You see the same sort of behavior continues, and you have a steady patterns that generates usually. So and as well as the usual U and V oscillating as such. So now you see that there is an intermediate frequency range that for which you see that at t equal to 400, if you look at this. Look at the figures, then the V actually settles down to a constant value at these cases. So both V and U settles down at constant value for the different frequencies. Say when omega equal to slightly higher, 0.02, 0.07, 0.0 up to 0.09, it remains almost in the all in the steady state. Now at some still high value, 0.1, we see that again oscillation gets restarted. So start from here, and it develops at some point, and you take a snapshot picture, and this, and once you have this again, and this continues up to this case, and you see that the same pattern reappears at this case, and this is for the 0.1. And this still continues. So this is again for the higher value. You have this continue. You will see the same pattern. The interesting idea is this, that there is an intermediate range of frequencies where the matching of the two transitions are such that the two transitions, one parametric oscillation, parametric transition, other for parametric excitation, other direct excitations, both of them interfere. And the interference is such that over a range of frequencies, that this particular interference actually particularly works. And that leads to some sort of deep in the anti-resonance spectrum, and you see don't see any sort of pattern, and the system remains stable in this particular frequency range. But outside this frequency range, you have the usual patterns as such. So that's interesting. So the idea is this, that not only in a coupled system where you have a destructive interference between the coherent drive and the coupling. When you have this sort of anti-resonance kind of picture that emerges. We can also have this sort of picture when we have the different kinds of transitions can interfere, so that there at some intermediate frequency range, this particular refractive interference dominates, and that leads to this sort of anti-resonance kind of behavior. So we come to the conclusion right now that anti-resonance now appears as a destructive interference between the periodic drive and the coupling that we started with. That is the usual notion, the idea, and that is a standard paradigm over which we normally work. And you have seen that there is a special kind of anti-resonance effect, and we call that it is a counter resonance to vibrational resonance. And this is basically the tuning of the interplay of nonlinearity and high frequency driving. That is, we can find out this sort of anti-resonance kind of vibrational anti-resonance kind of behavior when we have the response amplitude shows a sharp dip. As we plot this response amplitude as a response amplitude along with this the strength of the rapidly varying field for a definite frequency, high frequency. And spatiotemporal anti-resonance is observed when this destructive interference between the periodic drive and the coupling creates the stability difference between two subsystems. That's a very interesting thing. And this is particularly interesting when the coupled systems are spatially extended, and particularly reaction diffusion systems. And we see that that is a driven subsystem settles down to a homogeneous steady state, an undriven system shows a non-stationary patterns, and that's interesting thing. And spatiotemporal resonance can also arise, and that's an interesting thing that we discussed in the last case, that is the single parametrically driven reaction diffusion system as a result of a destructive interference of direct and parametric transitions. And you can see that this can open up the other possibilities of observing this anti-resonance kind of thing. And for that matter, it is some sort of a what is called a Fano resonance. And when you have there is a direct one-to-one interesting similarity with the Fano resonance in atomic physics, where you have the direct ionization of a deep inertial electron in an atom, say in a inert gas atom, and that channel, particularly that channel, actually interferes with auto-ionizing channel of the two excited electrons, followed by over effect kind of thing. So in that particular case, you will see that once you have when you excite one of the atoms to one of the electrons to an auto-ionizing state, and then there is an over effect that leads one of the electron to the outer one of the electron is driven out, and the other goes back to the original state. and that gives you a picture that there is another channel. So there is a direct channel and autoionizing channel. These two channels can actually interfere, and you see this Fano resonance, the Fano resonance deep. And this sort of the last example that we had seen actually inspired by this sort of Fano resonance kind of thing in atomic physics, and this may be considered as an this Fano resonance kind of analog in this case of nonlinear dynamics. So thank you all for your attention, and before I conclude, let me thank Prosun Sarkar, Krishnendu Pal and Shivashish Pal for their direct involvement in this work, and they are the main workers in the team, and with which I worked. I had the chance to work with. Thank you all for your attention.
Now, time for questions. Professor, can you read the chat box?
Yes.
Yeah, because it seems someone has raised in the chat box.
Hello. Hello, I'm Shamal speaking.
Sure.
Yeah. First of all, thank you for your nice lecture on the very interesting topic. Although it's not my field directly, do not work on this, but I understand by your lucid description of the models and the results. So my question is, when you showed the two layers, there is one is driven and another is undriven, and there is a communication between the reactions, and it finally started with an anti-resonance. One of the cases is anti-resonance between the layers, and
Yes.
one of the layer goes to the steady state, and another layer is evolving with a pattern. But so whether the undriven system pattern is stationary or is still evolving into different states?
If you mean undriven, no, undriven state goes over to a pattern state, means it is an unstable state, but it goes over to a steady pattern state.
I said that is my question. You say that it goes over.
It is a steady pattern state. If you look at the oscillation, that oscillation persists, but when you look at the patterns, you will see that the patterns are not changing in any way.
Yes, that is my question.
Yes.
Yeah, that is my question. So that is not a pattern is going stable.
Going stable. Yes.
Actually, my intention is to know that whether there is the pattern seems to be really spread out over the whole space of the one layer.
Yes.
But my intention is to ask this question: is there any intermediate localized pattern or not?
Intermediate localized patterns. So
not fulfilling the whole space. Yeah.
Yes, that may be possible, but that depends on the details of the system. The system we had actually studied is something has a structure that was this kind of either spot-like or the typical stripe type of patterns.
Okay, thank you.
Okay.
Thank you very much, Professor Ray. This is Lakshmanan. I suppose we have not met. It was a very interesting, very nice talk. I really enjoyed it. I have just a basic question.
Yes.
In your system, you say that it's a driven system. Then how do you say that you have homogeneous steady state?
Homogeneous, but when the system, I've assumed that when the system is not driven, homogeneous steady state
No,
is when it is not driven.
When it's not driven, it's fine. But your
Yes.
system is a driven one. So how do you start saying that you have a homogeneous steady state?
When I'm driving it, it is not in a homogeneous steady state. But the interesting thing is this: when the coupling as well as the driving operate simultaneously, then the system is getting in a stationary state. That remains, that one can see also from the numerical analysis, that it stays over a constant value at 0. But this is, but one of the things is not there, uncoupled system. In that case, it is that is when it is driven, it is never in a homogeneous steady state. It is that cannot be steady. I'm assuming that by steady state I means 1-0 steady state for the system. It is basically the when the system is undriven.
Yeah, but your system is driven. So
yes.
it doesn't have a homogeneous steady state, because in reaction diffusion equation you always start with an undriven system and you find homogeneous steady state and then you perturb. So it's not clear to me. I mean, how with the driven force, external force, you still start with a homogeneous steady state.
Yes, I have understood your point. That means whenever you say that whenever there is something driven, it is not that it cannot be in a homogeneous state. Yes, but I'm actually characterizing this for characterization only. I am use this particular 1-0 state. Otherwise, it is always driven. And that this particular value, that is FUGV minus FG, FU greater than 0, actually these stability conditions actually ensures that there is a frequency which is always positive and so on. And that makes the characterization of the steady state without any external drive. That is the point.
Okay, thank you very much. Thank you.
Okay.
There are some questions in the chat box.
Yes. So, is it possible to observe? Can you ask these questions? I'm actually missing some of the questions. Can you ask? There are some questions in the chat box, but I cannot see. Yes.
Maybe I will ask. Sudarshan, you can.
If you can ask some of them, then.
Yes, please. Yeah, Sudarshan, can you raise your question? Instead of the chat box. Yeah.
Sir, can you hear me?
Yes, I can hear.
Sir, is it possible to observe these anti-resonance phenomena in single systems without any drive, but which has both slow and fast timescales?
Without any drive. That is actually drive was actually applied to have you see that in the latter case we had a drive when we had a single system, but the drive is not an ordinary drive, it is a parametric drive, and that makes the system the transition, the two different kind of transition, one parametric transition, other is a direct transition. So effect of interference of these transitions are actually embedded, are actually captured in the anti-resonance. That was the idea, basic idea. So if you don't have any drive, then you cannot have this sort of this sort of interference. First and foremost thing is that some destructive interference must be there in the system. Otherwise, you cannot have any sort of thing in that way.
Okay, sir. Why I ask this question is because you told in coupled system when you will get by the external drive, it will make the coupled system, it will convert the coupled system into slow system and fast system. That is why I asked whether can it be observed in slow fast single systems.
Slow, fast, single systems, I don't think so, because once the timescales are completely separated, it is difficult to find out this interference. So once you have a slow systems, then you can have a interference effect in the usual way, and when you have a very fast systems and you have nonlinearity in the system, so there are different frequencies, they interfere with particular with the external high frequency field. So in that case, there is another kind of interference. So they are operating in the two different ranges of frequencies.
Okay, sir. Okay.
Actually, I had seen one of the papers by Rajshekhar, which was published quite some time back, when he had shown that Rajshekhar and some other person, I forgot the name. So they showed some sort of anti-resonance in Morse oscillator. So I was actually puzzled by it because it was a driven system. But then I realized that yes, it may be possible because there are transitions which are not really the direct transitions, and which are transitions which are maybe the this sort of parametric and intermediate transitions, because in a quantum systems, when you are trying to drive a system, they are multiplicative drive. So they are so in general they are of there can be parametric driving inside. So that's maybe the reason. So that's why we try to investigate it from scratch by Troy model first, and then we had gone over to this particular example.
Okay, sir. Thank you, sir. Thank you.
There is a question from MSc student.
Yes.
Haripalakrishnan, can you write now?
Sir,
Yes.
yes, sir. So, what is the difference between synchronization and resonance in coupled oscillators, sir?
So synchronization and coupled. Synchronization is something that the you have the coupled oscillators, and when but they are synchronized in the usual. They can be synchronized so that there are certain quantifiers which can give you the idea that they are synchronized as such. And if you look at the patterns, and you will see that they can be synchronized. They are synchronized at the beginning, at some point in the end. Although initially unsynchronized, they can be synchronized. But anti-resonance is somewhat different. Synchronization is basically it is not an interference effect in general. So once you drive the system by using some sort of parametric driving, one can synchronize the two systems. It is possible, but that scenario is somewhat different. That is not a interference scenario. So in that case, both the systems are actually oscillating. See, and here one of the system goes down to a steady state, although it is driven.
Thank you, sir.
Professor Dibakar, do you have some questions? Oh, it seems it's not. Cynthia, can you raise the question now?
Hi, sir. Good afternoon, sir. Sir, I have a doubt.
Good afternoon.
Sir,
Yes.
is there any effects of anti-resonance in doing experiments, sir?
Effect of anti-resonance?
Yes, sir. While doing experiments.
Experiments.
Yeah. Yes.
Oh, actually, this particular I have not seen any example right now, but it is possible to construct this kind of experiment. using this gray Scott model, because there are examples where the ferrocyanides, iodate and sulfite reactions are there, which were studied by Sweeney way back in 90s, and gray Scott system is particularly motivated by that example, the ferrocyanide iodate sulfide reactions. And of course, since iodate is there in the system, so one can use this drive, a coherent drive, by using the fluctuation of light, because iodate is photosensitive. Iodate generates iodine, and that is photosensitive. So one can use this sort of coherent drive from using external light source, and that has been done earlier in other experiments, other kinds of experiments. So it is possible to design some sort of experiment in using this sort of system, I suppose. But right now I do not have any knowledge that this is there is any experimental demonstration of anti-resonance in reaction diffusion as such.
Yes, sir. Thank you, sir.
Okay. Nisi, now you can raise your question.
Sir, is it possible to see this phenomena, anti-resonance phenomena, in coupled system without coherent drive, provided that the coupling itself induces some high frequency transitions?
Maybe it is possible, but I have not yet. I cannot say right now. It is. But if you can theoretically find out the possible reasons that any reason that yes, there are transitions which can be generated out of it, then it is possible.
Okay, sir. Thank you.
But another point is that since all the systems are damped systems, and effective system is damped, so although coupled, but if there is no drive in the system, then it cannot sustain for a long time. That is why the drive is also necessary. Otherwise, the damped system ultimately lead to a completely collapsed state. That is the point.
Okay, sir. Thank you.
Any other question? Cynthia, there is an answer to your question in the chat box also.
Huh.
Yeah. Okay. So, are there any other questions? All right. If not, let us conclude this session by thanking Professor Detuning Ray for giving a very interesting talk on autoresonance, starting from a single one-dimensional harmonic oscillator to infinite dimensional PDEs. So it is a very interesting talk. I think students have enjoyed the talk. So if students, if you have more doubts, please write to him. He'll be very happy to answer all your questions. So with this, I want to conclude. I want to wind up the session. Thank you, Professor. Thank you.
Thank you, Professor Centilvanian, for your excellent coordination and your invitation, and finally all of you.
Okay.
Yes.
I will write to you, sir. I will write.
Okay. Thank you.
Oh, thank you very much.
Okay. Thank you.